So for a given size of confidence interval, all we need to do is go to our normal distribution and identify how much of this distribution we want covered, and then see what z-score that's associated with. So a z-score of 0 is right there. A z-score of plus or minus 1 is from 1 to negative 1. The z-score for normal distribution is simply how many standard deviations away a given sample statistic is from the middle. Again, a z-score is just how many standard deviations away a sample statistic is from the middle. So, if we want a 90% interval, we go out 1.6. If we want a 95% interval, we go out 1.96. If we want a 99% interval, we go out 2.575 on the normal distribution. The magical thing is, and here's the magical connection, those bootstrap distributions are basically this normal distribution. That's all it is. It's basically the same thing. Now, you'll see that this isn't exactly what you've been doing. We'll get to that in a second, but that's the theory behind what's going on. Now, the example in here is for a population proportion. We're not doing that. There are some examples at the end that we'll get to, and I'll show you how to do this. But just, you can skip all the formulas here and all that other stuff. But just as a case in point, let me just quickly talk through this. If we want to find the confidence interval for a population proportion, well, we need to know the statistic or the sample proportion of interest. We need to know how far out we want to go, what level of confidence interval we want. So the z-score, the z-star here. And then we need to know the standard error from the sample we're working with. Well, in this case, to use this formula for a proportion, our sample size needs to be large enough such that, again, this is just, I'm just saying this to make sure we hit all the steps here. You're not going to be responsible for this. We're not doing proportions in here. And yeah, anyway, but you basically need a large enough sample size. Sample size times the sample proportion needs to be greater than or equal to 10. And the sample size times 1 minus the sample proportion needs to be greater than or equal to 10 to allow this formula to work for proportions. Anyway, so you plug in some stuff. This is just the formula for the standard error for the proportion of interest. And so if we are given a situation where a random sample of 1,000 adults were asked, do you favor or oppose sin taxes on soda and junk food? If we did a random sample of 1,000 and found that 320 of them responded in favor, how do we find a confidence interval of 95% sureness for the true proportion of all U.S. adults that favor these taxes? Well, we've got a sample size of 1,000. We will be able to find our proportion here in a moment. Our counts are greater than 10. That was the condition a couple slides ago. Again, you're not going to be doing an example like this, but I just want to make sure I reference these points. So for a 95% confidence interval, we just saw on the previous few slides that I can use a z-star score or a multiplier of 1.96. The formula is this monstrosity given here. And so the sample proportion is 320 out of 1,000, so 0.32. The 1.96 is the multiplier we use to obtain 95% confidence and obtain the proper width on a normal distribution. And the formula for standard error for a proportion is just this thing, the proportion times 1 minus the proportion divided by the sample size, square root. So we just plug in the numbers. We get some formulas here, we get some math, and we obtain a 95% confidence interval on this population proportion of about 0.291 to about 0.349. Usual interpretations, again, there's really nothing new here in terms of interpretations. It's just how do we get to the number? So we're still 95% confident that the population proportion is about 0.29 to 0.349 for U.S. adults at this time who favored sin taxes. If this were to be bootstrapped, if we were to bootstrap this to find the confidence interval and simulate our repeated samples, our repeated proportions from our samples, we'd get about the same thing. And this is a great proof in concept right here. We can use our Z interval to make the confidence interval using the assumption from the central limit theorem, or we can bootstrap and get basically the same darn thing. Now, here's the thing. Central limit theorem allows us to do this given a particular population mean and given a particular population standard error, which requires a population standard deviation. Okay, here's the big math step. You're not going to have to calculate this, but here's the big math step conceptually. Remember this standard error that we've been working with, that thing which quantifies sampling variability, that thing you've been getting from the bootstrap distribution? Well, you can estimate that with a formula. That formula is the that formula is the standard deviation of the population. That is, yes, the standard deviation of the entire population divided by the square root of that n, the sample. That gives us the true estimate for the sampling variability, the true measure of the sampling variability in this case. So it's the true population standard deviation divided by square root of n. The problem is that we do not know the population standard deviation. Why do we not know the population standard deviation? Because we did not ask the entire population. If we were able to ask the entire population about the thing we're interested in, we would not need to be doing statistics. We could just ask the entire population of interest the thing we care about and measure it and be done. But we generally don't do that. So we don't have the population standard deviation. So we need to estimate that. How do we estimate that? By taking the sample standard deviation. Just like you've already done with your descriptive statistics. You get a sample standard deviation, and a sample size. We call that sample standard deviation S. That is an estimate of the population standard deviation. And then we can use that to estimate what the standard error is for our situation. Again, the standard error is a representation of how much sampling variability there is if I'm meant to repeatedly sample from my population. So, here's the thing. The central limit theorem was great because it said our sampling distribution was completely normal. Well, if we can no longer use this population standard deviation and we have to approximate it, we can't use the normal distribution anymore because we don't have the population standard deviation. I have something different. I have an estimate. I have the sample standard deviation. So I can't use the normal distribution anymore. Instead, I use something called the magical t-distribution. Or it's just called the t-distribution, but it's really magical. What happens when we estimate things using our sample, what we use for our confidence interval and to get our p-values for things is something called a t-distribution. As you will see, it is super similar to just our usual normal distribution. It's shifted a little bit, and it also changes shape depending on the sample size. So, here's the thing. the t-distribution generally looks normal, but it changes shape depending on the sample size. The closer our sample size is to the population size, in other words, the higher our sample size, the closer to the normal distribution we will get, which should make some sense. The closer we are to our population, in other words, the more cases we're able to take, then the closer our distribution will be to the normal distribution, which is what we had from the population in the first place. The way we characterize this shape change, depending on sample size, is called degrees of freedom. And degrees of freedom is a whole separate concept I'm not going to get into here. I would want to talk about that separately. But it's a way to measure basically how much information we're getting from our sample. That's a very, very loose interpretation, but I'm just trying to give you something to latch on to, because degrees of freedom is a very mouthy, garbly term. People use it a lot. They don't really know what it means. Degrees of freedom is just a way to represent basically our sample size and whether or not it's high or it's low. And it has a very particular kind of calculation. Point being, the higher our sample size, the higher our degrees of freedom within our data, and the more our t-distribution changes. So as a proof of concept, the normal distribution is in this black line, the standard normal, with a mean of 0 and a standard deviation of 1. A t-distribution with degrees of freedom equal to 5 is in red, and we can see that it's a little bit lower in the middle, and it's got bigger tails. And this is to account for the fact that there's uncertainty coming from the fact that we're using a sample. If we weren't using a sample, we would have more uncertainty with what was going on. The larger our sample we have, the more certainty we know of what's going on. Therefore, as the sample size increases, or as we say, the degrees of freedom increases, then our t-distribution starts to become a little thinner in the tails, as shown in the blue line down here, and starts to more closely approximate a normal distribution. Again, we use t-distributions because we cannot use the normal distribution because we do not know the population standard deviation. All this terminology and theory and ideas and the formulas, this is why traditional methods can be very taxing for people and a big black box for people. This is why simulation methods can be a lot more tangible and palatable as people are learning these things. So what this means is that there are an infinite number of t-distributions. It just depends on what your sample size is, and the t-distribution will shift accordingly. It has a formula, and this formula starts to describe the t-distribution. I'm not going to sit here and talk about this thing. I just want you to see it and start using it, and I think that way you're going to get a lot better experience about it. Learning math and things like this through some abstract thing like this, where it's not really being derived, that's not the most helpful thing. But I want to throw this in here. So if we've got a population mean and it is sufficiently large enough, n greater than 30, then instead of getting a z-score, we will get a t-score, and it's calculated by this formula involving the sample mean, some estimate for the population mean, the sample standard deviation, and the sample size. And this little formula here, in terms of how we convert our samples into t-scores to land on a t-distribution, is captured here. And so this little formula here captures the shape that this t-distribution has. Now, you will use, you're not going to have to calculate this by hand. That's the most important thing I need to say. You're going to get this from the software. This is the formula of things that are going into it. And now pause here as we move on to the next part in this video.